I'm going to start off with some introductions for those of you who don't know who I am. If you don't, I hope you would by now, but if not, I hope you get to know me soon. My name's Philip Morrow. I'm an applications expert here at MLC CAD Systems. I've been doing this for a little over 7 years. My background is in mechanical engineering. I worked in defense contracting industry and in a CNC machine shop before I came over to MLC. And really before then, I didn't use the MLC resources. So I hope after this, you'll know more about them, know how to contact me, know how to use our tech support and training and all the different web resources we have out there, including our YouTube channel. So if you haven't talked to me on the phone before, you might be recognizing my voice from our YouTube channel where I have a lot of flow simulation videos there. I encourage you to go check those out. Of course, I'm located in our main Austin, Texas corporate office. This is where most of us are, but we're spread out across the South here, and our technical team is all dedicated to supporting, training, and doing consulting services type work for SOLIDWORKS. We keep ourselves on the cutting edge by taking a number of technical certifications that are sponsored by SOLIDWORKS Corporate. And I just want you guys to know that you can do that as well. There's a number of public ones out there. In fact, if you're a subscription holder of a SOLIDWORKS license, you can take 2 free certification exams a year. We take a lot of them. There's a whole lot more on the internal side to be licensed to train and do different things with the software, which we've been doing for 38 years now. Every single release of the SOLIDWORKS software and more. Because really what we do is not just SOLIDWORKS at MLC. I'm talking about us doing training, product knowledge webinars like this, services, jobs, but we do this for really critical business needs that we see in the engineering company workflow. And it puts us in a unique position to really see out there how engineering companies are getting products to market. What tools are they using? What tools do we see in the industry that we think can remove bottlenecks and basically get us from A to B, get us to market faster? So if you really have a question, really anything in the engineering workflow, engineering business model that you want to ask us about, if we don't offer the tool, we've probably got the network and can put you in the right direction. So give us a call. That's what we're here for, is literally just to help you be more efficient. And I mentioned we're spread out across the South to do this. So I know we're doing a lot of online meetings nowadays. We're going to do a lot more things digitally. But rest assured, we have a technical person, a bag carrying person near you. Should you need somebody face-to-face, should you need somebody to get hands-on with a server or an in-person training class, that's available as well. Okay, so that was a real quick introduction here, 3 minutes for you guys, because I know a lot of you here today know who I am. I see Richie joined up, Ian's here. So I want to get to the meat of what we're talking about today, which is flow simulation. And the first thing to recognize about flow simulation is, like any tool with the SOLIDWORKS brand on it, it is connected to the same data, the same file. So when we're talking about, I don't know, anything from even data management to your counting, pulling a parts list to photo rendering, we're all connected back to the same file. So if we make a change in one place, it's up to date everywhere. And that's exactly how flow simulation works as well. It's also built inside of SOLIDWORKS, so it has the same interface. So when you think of a sim product here, or really anything with the SOLIDWORKS brand on it, the idea is to get more of these processes to work in parallel. Not just the data management, the messy multiple files and revision, but as soon as somebody creates a shape, well, I can start a flow simulation with that geometry. We can use configurations on it if we need to, and so if there's a change in the design, I know it's time to just rerun the flow simulation, and that's what we're talking about. So let's get to the actual software and what this thing actually is. This is a general purpose computational fluid dynamics tool, or what you're going to see a lot as CFD. Right, and in CFD, we're always coupled with heat transfer. So it's always doing convection heat transfer, even if you don't need it, that's in there. And this is built inside of SOLIDWORKS. So you need a SOLIDWORKS license to run this, but it just runs as an add-in with the same interface, the same right-click menus that you're used to. The idea then is you can use this as a design tool. You can use it to simulate performance, optimize performance, and compare designs side by side. That's really where the sweet spot for this is. It does not matter if you're talking about internal flows, external flows, or both happening at the same time. In fact, you could run compressible and incompressible fluids, even non-Newtonian fluids in here. So your slurries, your bloods, your different materials that act in these strange behaviors, not a problem. This software runs the K epsilon model for turbulence, meaning we don't need to specify where we have laminar flow or where things are transitioning. Really, it can handle all of that by itself. And I mentioned it was a heat transfer tool for some different reasons I'm going to talk about. Flow simulation, or CFD, computational fluid dynamics, is the best place to do heat transfer solutions. Whether that's conduction, radiation, or just convection, which is always being solved. And for those of you who know SOLIDWORKS simulation, without the word flow in there, that's our finite element analysis, our stress and deflection software that's also built in. These two products work together, they're coupled. So let's say you run a flow simulation and you've determined a pressure distribution on something outside in the wind, or a temperature distribution, and things are going to expand as they heat up. Well, you can take those results and use them as an input over in SOLIDWORKS simulation and calculate those deflections due to the wind loading and those stresses due to thermal expansion. So as you'd expect, the tools work together. This also means over the 7 years I've been here, I've seen them in a lot of applications, and I've seen the product grow. You guys know SOLIDWORKS, every major release comes out with 250 enhancements just to CAD. Well, this stuff happens with Sim as well. The release is a little later, so you might have missed some of these really cool capabilities that came in, because they actually show up usually around the February timeframe. One of them you definitely should know about is optimization. Whether that's just a what-if side-by-side comparison or like a multivariable design of experiments, you can use this software to optimize towards a goal. Let's say, what length of pipe do I need to achieve this pressure drop? Well, we can have the software figure that out for us. You can also do solution adaptive meshing here. That's the ability to pause the solve and have the software increase the mesh density in areas where there's high rates of change and high gradients, basically just giving you a more accurate solution and a more efficient mesh. It's really something you couldn't do manually, something you want the software to do for you. Additionally, a sliding mesh capability has come in. This is perfect for rotating geometries, to actually spin those mesh cells, which are representing impellers and fan blades and wind turbine blades. And another really cool one, you definitely see this across our YouTube channel a bit, free surface. That's the interface between two fluids that can't mix. So we're talking oil and water, water and air. You want to see waves sloshing on top of a tank. That can definitely be done in here as a transient time-dependent study. Finally, we're doing pressure plots as well. So of course you can do noise prediction in decibels. Pretty cool if you're doing something like a Flowmaster exhaust, or how about a suppressor? Great place to design those types of things. So yeah, the use of this software is far and wide, right? When I think, okay, I'm going to show today some flow simulation, some hands-on with the software, I'm thinking, okay, what do I want to show you guys? This could just be pressure chambers. It could be spinning and rotating things like the hairdryer model. It could be lighting applications, especially for high temp things like radiation, halogen lights, or just LED housings, or air conditioners. And we're running like humidity models and figuring out comfort parameters. Really, the origins of this code, when it first started to be written back in, the late 80s, this was for rocket nozzle design. For high Mach number flow was the original stuff. So drag forces, boundary layer skin effects, aircraft design is a perfect place to be. And that kind of goes in to automotive stuff. Of course, drag forces for race cars. We have NASCAR teams, the US bobsled team that uses this program. Sloshing inside of a diesel tank, which you could see on our YouTube channel. Or those comfort parameters I mentioned again to figure out how effective could your HVAC system be. And then there's some niche things as well. Porous media effects could be used for air filtration systems, catalytic converters, or figuring out exhaust manifolds as well. So I've got a lot of stuff to choose from when I get to talk about flow simulation. It's like the coolest simulation software that SOLIDWORKS puts out, I think, because it's so far-reaching and the visuals that come out of it are just awesome. So I'll tell you why I see it used most in my area, and our customers that are here in Austin, Texas. And the first one is just figuring out the airflow dynamics, which are often counterintuitive or have some kind of physical phenomena like the Kawanda effect or something going on that we wouldn't have guessed if we just built it and prototyped it. A common example I use is the old, is my truck going to be more fuel efficient on the highway if I've got the tailgate up or tailgate down? To me, it feels like the tailgate down would be the way to go. We maybe have less drag than that vertical tailgate back there. But really, it's not the case. It's the opposite. What you find out when you run this in Flow Sim or in a wind tunnel is that you get a stagnation of vortexing air in the bed of the truck. This works as what's called a virtual body. Because it just sits there, it allows the rest of the air to flow over that virtual body and just stream over the top, basically reducing the drag force. Sometimes stuff like this happens, even inducing turbulence. The bumps on a golf ball can be counterintuitive. So definitely the first reason I see this used. But the second big one is thermal analysis. This could be for large industrial applications, but I see it a lot in tiny electronic devices that maybe have forced convection, maybe have free convection, but have a lot of little components that are heating up that would be difficult to mesh in a traditional finite element analysis program. And because we don't have to make the same assumptions over in flow simulation, we don't have to have fixed ambient temperatures. We don't tell it the rates of convection. It calculates these things. But the only downside maybe is that the solves are a little bit longer because we're getting more information out of it. So with those two ideas in mind, I thought I would show you guys today two different scenarios. I know I'm talking a little fast because I want to show you both of these. The first would be an exhaust recirculation. Sometimes you see these called preheaters, right? We take exhaust off of one thing, bleed it into the incoming air of another. And of course, it's really important that that exhaust comes in evenly mixed since you're kind of polluting the air downstream just to warm it up. So we want to see, could we make some changes to this design, or how good is it at mixing in that hot exhaust into a new stream of air? And then, of course, electronics cooling. I've got a model here that uses just free convection, some heat generated by LEDs, and just take a look at how one way that we might solve that using external analysis in the software. So those are my two thoughts for today. Let's start first with the exhaust recirculation manifold. This one has just a few components, and I can show you completely the setup of it because that's the first step here, right? Let's just take our CAD model and set up the experiment that we're going with on the exact same model. You can make another configuration if you need to, but you could just work in the same assembly that you've got right now. With flow simulation, there is little to no need to do a bunch of geometry simplification. You can just get going. So here's the product I'm gonna work with here. What I've got is on the right side, just kind of open to the atmosphere, and on the left side, I've got inside of this gray an exhaust gas coming in hot, and I know the mass flow rate of it. On the bottom left side here of this gold component, I've got air just coming in, 40 degrees C, a little warm, and I know the mass flow rate of that as well. So I want to achieve some sufficient mixing here and see what these temperatures are going to be at the exit here as well. Now, I do this in flow simulation with a wizard. This is the only software that I use a wizard every time. And I know the software well, and I still use the wizard every time. So let's flip over and I'll show you what this looks like. So here in SOLIDWORKS, I've got my assembly open. It's just a regular assembly you deal with. The only difference here is that I've made the assembly semi-transparent, and I've actually capped off the openings. And I did this to make an internal flow. So there's some flow sim tools to automate lid creation. Click a face, and bang, I've got those things capped off, and I'm ready to start a flow simulation. Now, you guys see already that the interface is the same, right? I've got a command manager on top, and I've got a flow simulation tab. It is added into the software, and I'm just going to launch the wizard straight off of that. So the wizard will help me set up this project. I can give it a name like a exhaust mixing manifold. I'm going to use just the current configuration, but these are configuration specific, which is very handy. And then I'll pick a system of units. You're going to find anything you want here. I'm just going to change the temperature to Celsius. And of course, you can save this so you never have to do that twice. Now let's set this thing up a little bit. This is an internal analysis. I don't have any hollow cavities in there, so really I just need that. I'm not going to do heat conduction this time, but here's where I'm turning on more equations for the solver. So the less things I check, the faster it'll solve. This thing is dominated by flow. Gravity is not even going to be that important because we don't have natural convection. So really, I'm just going to run internal analysis. I know convection and all my flow velocities and pressures are solved. So that's it. I'll just hit next. Now, depending on what I chose there, I need to tell it what are the defaults. What's everything going to start with? And well, I'm going to say, okay, I've got air in this analysis, so I'll just open gases and add air. I've also actually added another gas of my own here to represent exhaust. You can add any custom materials you want, of course. So these two fluids are going to be in my project. I'm adding both of those. Because I chose gases, I've got some extra options if I needed them, like run a humidity model or run high Mach number flows. But I don't need to add those equations here, so I'll just hit next again. Default wall conditions make sense to me. The only way heat's getting in or out is by the entrance and exit that I tell it. We have a no slip at the wall assumption. So you'll notice I'm not making many changes in this wizard, am I? The only thing you really got to know about is answer the questions for what you need, and everything here becomes the default for your initial conditions. For instance, I've got a concentration section. Let's say, hey, initially everything is 100% air, unless I tell it otherwise. That'll become the default, and I'll just hit finish. All right, so that wizard, I use it every time. You add the things you want to know about and what's going to be in here overall default, and then you've got some starting conditions to deal with. Pretty simple. I never skip it. But now we get to the individual stuff. Now we need to go around and tell it what are my ins and outs and what's different from the wizard. So for instance, I know I've got an inlet mass flow here of 0.009 kilograms per second at 280 C. How do we set that up? Well, Flow Simulation made a new tree. Here it is. It's got my exhaust mixing manifold. It's got my simulation set up. If you use SOLIDWORKS now, you guys definitely know how to use trees. It also created a computational domain for me. That's that cube you see. So it recognized the volume that I'm working in. I could use this to specify some symmetry if I needed to, but I'm just going to hide it because it looks good. And my ins and outs are what's called boundary conditions. So I'm going to insert a boundary condition, and I'm simply going to go choose the inlet face. Here I'm going to use a quick little select other to get the inside face of that lid that I made, because what I know is an inlet mass flow rate of 0.009. And then there's a lot of other buttons and things in here. There's a whole bunch of stuff. I mean, I could go to the help file and read what all this stuff is, but all this stuff is just going to be as I said it was in the wizard. So I said everything was air. If I expand substance concentrations, it says, hey, this is 100% air. Well, I'm going to switch that so it's 100% exhaust. And if I look at the thermodynamic parameters, hey, it's the room temperature that I left in the wizard. I'm going to make that 280 degrees C. So if you forget something, if you don't know what to put down here, don't worry about it. It's just going to be what was in the wizard. And then one green check, and I've got my inlet. Similar thing is happening over here with air. If I quickly flip back to our experimental setup, looks like I've got air coming in just at 40 degrees C and 0.05. So I'm going to insert another mass flow rate coming in, 0.05. I'll just grab the face that air comes into the system at. And really, I don't need to change the substance concentrations, anything else here. I can make it a little warmer. It comes in at 40 degrees C. All right, that's pretty good. And how about the outlet? That one's probably the easiest boundary condition, because now instead of a known inlet flow rate or an inlet velocity, I can just say this is a pressure opening. This is just open to the environment. So it's just going to spill out into air that's at 1 atmosphere and room temp. So that's my exit over there. Not too complex to figure out the ins and outs of this entire system. Now there's one thing over here in my experimental setup on the right that I could skip, but you really shouldn't. These are goals. What are you looking for in this? By specifying goals, you're going to get those outlets, those numbers just delivered to you. So it's great for post-processing, but it also helps us check the accuracy, right? We got a garbage in, garbage out scenario. I want to make sure that the numbers coming out are what I expected, that I set things up right. So I'm just going to right click on goals. You can do these per body, per specific surface. Maybe I'll just say globally, let's find out here. And you get a whole list of stuff you can use. Let's say globally, I want to know what the average fluid temperature is. And I'm just going to create that goal. So that'll be monitored during the solver. The solver will know that's something it needs to be particularly accurate about. Plus, I get the hard numbers out, as a result from this thing, which is going to be super nice. At this point, I'm actually ready to run this thing. I went through the wizard. I specified how things come in and out of my model. I set up a goal that I'm interested in. There is a section here on meshing, but honestly, this is very simple geometry. A couple tubes, they don't change much in diameter. The mesh it comes out with is going to be fine. And if you're really interested in the details of meshing too, well, that's what we spend about half our training class over. So definitely let us know about that. One thing I want to point out is if I run this right now, I can leave a couple of CPUs open on my computer to do other things with. And I can pick up old calculations and continue ones that I stopped and left off. So I mentioned that when you're running one of these, it might take a little longer than FEA. Well, that's okay. You can actually pause one of these and come back to it later. You could leave yourself some CPU available, so you can go on, Google Chrome, whatever you need during the day. You can even offload this to a slave computer and just have it run on your coworker's machine, and they can wonder why their CPU is running so hard. So, I mean, that's simply it. Set up an experiment using the wizard, your ins and outs, and hit run. You guys all know how to use a tree, and you know how to use that right-click button inside of SOLIDWORKS. You're going to be able to get one of these running. In fact, I did something here that you really don't see done in web demonstrations of software. I actually hit run on this model so that it's cranking up right now, and it's loading all those things that I set up into these big math equations, preparing that. Then it's going to mesh the model, break it down to those cells, and start solving. The reason I hit run and decided to do that here live is because I wanted you guys to see this solver window. Everyone kind of knows that flow sims, CFDs take a little longer to run, but I'm just running this on my Lenovo laptop. And I've already mentioned that you could save yourself some CPUs, or you could stop one of these and pick it up later. But you also get real-time feedback as you're solving these things. So what if your setup was a lot more complicated? Well, in something like this, it's already solving here. I'm actually going to pause it. I can see what's going on with the solving. Do I have any warnings I should know about? I could monitor that average temperature that I set up as a goal. I can see it's increasing. And I could even watch cut plots of this model. So I could say, let's just pick a plane and watch, let's watch velocity, sure. And you can see there's my plane just kind of cuts through it in 3 different spots. And so if I unpause this, I can see things change from where they were at my initially all air-filled room temperature to as this flow starts to develop. So if you get something that goes, the wrong direction, okay, I must have set something up wrong. I can go ahead and stop this and just go back in and make a change in the software and pick right back up from where I left off. So don't worry about these long solve times. It's really a misnomer. You're going to get results out of it right away. Even while it's solving, I'm making cut plots. I can save animations of those, and I can get qualitative and quantitative results out of it. But these are the type of results you get once you get your results back. And this thing solved pretty quick, but I did solve it ahead of time. So I'm just going to switch my studies here. I'm just switching over to one that I set up ahead of time. You notice I created a few more goals, but that's it. And I look down in the results section. Now there is so much you can do in the top half of a results tree in Flow Simulation to show off what you've got. Cut plots with streamlines that you can animate and move through your computational domain. If you're interested in these, there is an awesome video on our YouTube channel that just says results visualizations and shows you how to make animations of all this stuff, show multiple ones at the same time. Here I've got a surface plot showing the outlet profile by mass fraction of exhaust gas. And this is actually telling already. Even though we're qualitative, what I can see here is I've got a high mass fraction of exhaust gas just sitting on one side. So not very evenly distributed. I'm a big fan of moving through cut plots and surface plots first to really learn about what the flow behavior is. You're not going to miss anything here. And I can see, okay, my velocity's out here on the surface, and where I've got my mass distribution. How evenly is it flowing? After you go through some of these qualitative things just to learn about them, make sure you kind of understand that this is working the way you intended, and if there's any phenomena you didn't realize, then maybe set up some flow trajectories. Flow trajectories are a super cool way to explain the flow to other people. And these have great animations where we can simply pick a face and say, hey, I want some arrows to move through this thing, maybe color them by mass fraction of exhaust gas as they are here. They're always going to move with the respective velocity, and they just make great animations that if you show them to anyone outside of engineering, they're immediately going to understand, what this really means. Of course, once you get through there, it's time for the hard data, right? To actually get some numbers out of here. And that's where the second half of this result tree comes in, where you start dealing with goal plots and volume parameters. I'm actually going to jump straight to a goal plot. So I mentioned if you set up those goals earlier, you could see them immediately in Flow Simulation. Well, here, let's take a look at all the different goals. We're looking at mass fractions of air at the inlets and outlets. We're looking at a global goal for average temperature of the fluid. And if I just hit show, all these numbers show up right down here. So I can see what the answers are right away. I can see that average fluid temperature is above boiling point right here. And I can check out what their deviation is. You could also check out their convergence graph. So as this thing solved, was it still bouncing around, or did it converge and get me a good output given my input? So I get a nice sanity check on the efficiency and accuracy of my setup, plus I get the hard numbers. In fact, when it comes to hard numbers, if you just hit export to Excel, you can see this takes, a couple of seconds, and you're going to get all the hard data output to Microsoft Excel. Here's it popped up for me. I've got that same table with more decimal place, plus all those nice convergence graphs plots. And of course, if you go all the way down, you've got the hard data. So if you want to do some more unique visualization, it can be really nice for transient, time-dependent stuff. You've got that as well. There's even an animation suite down here at the bottom. Now, if you forgot to make some goals, don't worry too much either. That's where these point, surface, and volume parameters come in. For instance, here's a surface parameter that's looking for the mass fraction of exhaust at the outlet surface, right? We can do this for anything even if we didn't set up a goal. You can do it for surfaces like that, for entire bodies, or one that I really like is point parameters. I can say evenly space 20 different points on a face and give me the value at each one of those points so I can compare what's their average, what's their standard deviation, and I can see all those hard numbers for each one of those data points. So qualitatively, quantitatively, it's all here. It's in a tree that I generally just work from top to bottom. Of course, all this can be saved out in a nice report, but I've just taken some screenshots here to show you the different behaviors. Here I've got flow trajectories using pipes, and we can see that mass fraction, just like you saw in the surface plot. It's really kind of just on one side, this exhaust gas. It's not great. If I average out some of these point parameters, I see, yeah, there's a lot of exhaust gas at one side of the exit, and there's a lot of air on the other side. There's not very even mixing. That shows up in the numbers when I look at those points, when I compare their standard deviation. And when I look at the hard goals as well, I can see, okay, maybe there's something we could do to improve this design. That's always the question, right? Okay, we know where we're at now. How do we improve this thing? Is there something we could optimize? Maybe we know we could change the diameter of something. Well, in this case, I'm thinking, let's just try some different pipe designs, because we could say what we've got now, we could extend that lower into the stream of incoming air, right? So it's right in the center of it. Or we could even turn it, which that seems to me like it would probably work best. We turn it, and then it's really already heading the right direction, and it's in the middle of the stream of air. That's probably a great way to go. Well, I mentioned these were configuration specific, right? And just like I actually said on units as well, if you do something twice in SOLIDWORKS, great reason to call us on tech support, because I guarantee there's a way to do it once. And this is the same thing here. I simply clone a study and turn it into another one. What that looks like in the software is simply right-clicking on a study and hitting clone. This is also how you start that goal optimization. But just right-click and hit clone. I can give it a new name, and I can pick which configuration I'm trying to clone it to. So that's what I've done. When you see here under these configurations, I've got my default, my extended, and my turned exhaust on here. So we can compare them side by side. When you clone, not only does it have the exact same setup, it's got the same plot outputs ready to go as soon as that's run. Now, if you do a lot of the same geometry, I'll say if you're just doing valves all day or something and you have separate files, you can save this as a template, a full template. But if you're using the same file, just use configurations. It's a super easy way to go. And of course, as you can imagine, when you hit run, we now have a batch run capability. So I can say, run these specific studies, just crank away. I'm going to lunch. We'll come back and compare. And you can do exactly that. When you right-click your results folder and run a comparison, all of those plots you can choose to see side by side. So what I'm showing you here is just the results comparison output of the surface plot at the exit. We're looking at mass fraction again of exhaust gas. So we can see the default one that we started with. We can see just extending that pipe a little bit in the middle. And then actually the one I thought would be best was extending and turning the pipe into the flow. But I can see here that it actually still creates, one concentrated area of exhaust gas. So it actually looks to me just qualitatively the most evenly distributed by just simply extending that pipe maybe 1 inch down. Not really what I expected. And of course that turns up in the numbers as well. We want the mass fraction of air and exhaust to be as similar as possible. So basically we want these bars to be the same length if we can. And that's what I'm seeing here with the extended pipe design. This is borne out if we look simply at the goal plots. We look at the overall range and the mass fraction here. So we can quickly say, okay, I know which pipe design is going to be best now. As a design, I can just add a 1 inch link to this and have markedly better downstream performance. Now, I hope just now I showed you how anybody could use this software, but I just used something with 2 inlets and an outlet, right? But I use the same geometry I'm using in CAD. I use the wizard, I specify my ins and outs, and I run it, and then I just play with the results tree from top to bottom, maybe using our results YouTube video, our visualization video as a template. Not too hard to do. Things get a little harder when you start going, well, what if I have 3,000 components here? What if I have an electronic design that has a lot of items on it, or just something that's going to take more clicks to set up? So I want to show you that with this electronics cooling design. Generally, we have a lot more components there, but it's still kind of small scale, so I can show it kind of nicely here in our web demo. And the geometry that I'm working with is a box for a smart LED ambient light sensor, the kind of light that would turn on when you walk into the room, but give you some nice color options, and probably control it like a Philips Hue or something like that, which are also guys actually who use Flow Simulation for their LED thermal analysis. So this started off, as an idea, as a napkin sketch. It's one of those where, the concept came together first, and actually the industrial design came together on this one first. So I wanted to show you an image of it. These are a couple screenshots from the program X-Shape. It's actually not SOLIDWORKS. It's a program that's owned by Dassault System. It's a cloud-based program on what they call the 3D Experience platform. And what you're seeing, why it has a lot of lines and faces in here, is what's called sub-D modeling. You can use push-pull modeling. It's basically an easy way to make ergonomic industrial design shapes without having to do all the hard, fully defined sketching you might do to parametrically define surface modeling in SOLIDWORKS. So if you're interested in something like that, it is a brand new thing. Get out there on the web and YouTube up X-Shape on the 3D Experience platform. That's how the concept art, the first initial design of this was created. And, it works with SOLIDWORKS. It's a Dassault Systems product, so it comes right from 3D Experience into SOLIDWORKS. Just like FlowSim and everything else, there's nothing SOLIDWORKS related that isn't going to be connected to that single piece of data. So when we bring that down into SOLIDWORKS, now we can get the real work done, not just the art, but we can do the board layout design. SOLIDWORKS actually has a PCB design program, SOLIDWORKS PCB. And if you're using Altium, this is powered by Altium. You can just buy a SOLIDWORKS PCB connector. So gone are those days of just like saving a step file and opening it in SOLIDWORKS and designing your housing. These things are bi-directional and they communicate back and forth with the board design team. So I'm not a PCB guy though. That work got done for me. one thing I want to point out, if you have a really large circuit board and you need to get this into Flow Sim, you might be wondering, well, I've got 3,000 components that generate heat. You can automate this as well. A real classic way of doing it is using CircuitWorks in SolidWorks. And CircuitWorks can contain the defined properties from those ECAD files, like the specific heat, the thermal conductivity, on a component level basis in a library of components. What that simply means is when it builds the board in SolidWorks for you, it creates that assembly, it will assign custom properties to those components that have specific names, right? Heat source, all one word, capital H, capital S, right? Has specific names that can be read by Flow Simulation. The reason this is really cool is because you don't have to do this stuff manually. Now, you could even do this part manually. You could build your own library and you could give it these custom property names. But when you get into Flow Simulation, you can simply hit import data from model. This is now going to look over your model. It's going to pick up things like, hey, is there a material in the model? Just a regular SolidWorks material. Bring that in. But it's also going to read those custom properties so it can bring in things like those heat generation rates. I'll show you what I mean. It's simply in the drop-down menus under the Flow Simulation tools, or if you right-click in the tree, just about everything's on a right-click, right? Hit import data from model. It takes a couple of seconds to run through the whole model. You can check the things that you like, that you want to bring in, and hit import. In this example, there's 123 different components that are generating heat, solid bodies generating heat, and they're all imported here in a couple of seconds, as well as a long list of solid materials. So again, if you're ever doing something twice in SolidWorks, give us a shout. There's a way to do it once. But let's flip over and take a look at the rest of this setup, besides just the automation of this setup. So notice here, I've already got this done. I've got a couple different projects as well to try some side-by-side items. But here's my Flow Simulation tree. It's got a few more things in it than my last tree, a few more components. If you ever right-click your tree, you can actually see a long list of all the different things you could stick in a Flow Sim tree. There's a lot of them. It's got a lot of applications. But luckily, whatever you fill out in the wizard is going to put the appropriate things in the tree for you. In fact, let's take a look at how the setup of this was done in the wizard. So what I'm dealing with here is an external analysis. I'm doing free convection, so I wanted the air around this box as well. But I'm also calculating heat conduction in solids, and I've turned on gravity. If you're doing free convection, you need things to get less dense and to rise, so you probably ought to turn up gravity. For the fluids here, we're just running air, but I've also turned on a humidity model. I figured it'd be a good idea to do that just because I'm dealing with electronics. Now I've turned on conduction, so I need a default solid. I'm just going to pick one. High impact polystyrene is what I'm using for the default solid. So everything becomes the default from the wizard until I tell it individually in the tree that it's something else, or I import that data from the model. Finally, my initial conditions are just room temperature, but I can specify things like an initial humidity and initial temperature for all of these solids. Again, the wizard did all the work for me, so I can just review the tree, ensure that I'm happy with the larger computational domain here, that I'm going to be able to see the heat rising that I want, drag this around to the size you need. I specified a few different solid materials inside of here, some silicon, some steel, some copper, but everything else is going to be this polystyrene thermal material properties unless I tell it otherwise. Now I kind of skipped boundary conditions because I don't have any ins and outs, right? It's an external analysis, so as things get hot, they should just rise, but I have specified two heat sources. Just solid bodies. This represents each one of the LEDs and a couple of capacitors. Another way that you can deal with LEDs is by treating them as an integrated circuit. So you can calculate a junction and a board temperature. This requires an electronics cooling module add-on I'll talk about later, but this is what it looks like, a 2-resistor component. There's a lot of built-in integrated circuit chips we can choose from out of the database that Flow Simulation comes with. It's a nice, accurate way to deal with those. Similarly, the same thing comes with a PCB. I could have said this is just simply a piece of FR4 board, but when you're dealing with fans, integrated circuits, 2-resistor components, there is a huge database to provide more detailed information about this stuff. That's where I'm grabbing materials. That's where I'm grabbing these things. And you can see here I've got a more accurate representation of my PCB and the percentage of copper covering each layer. In fact, if you wanted to go all the way up there, using something like SOLIDWORKS PCB, which will actually model you those traces if you wanted to, you could then apply Joule heating and figure out how much the copper is going to heat up with currents flowing through it. But I figured that was overkill here. I just need a PCB. I need some stuff that's generating heat, and I need some goals. What am I looking for here? The average and max solid temperature. And I wanted to know globally what's the max velocity that I get out of this thing just from the heat causing air to rise. Now, in the initial setup of this, there's actually no vents. I just wanted to know how hot does this thing get? And it didn't get crazy hot. It would probably still function as long as you didn't take it outside in Texas at any point in the day right now. It'd probably still work, but obviously we need to put some vents on here, and the question becomes, where do we want to put those? Not yet an optimization, but some ideas on here, right? Let's say we just put the vents up at the top, maybe not on the very top, but a little bit back, so water didn't run straight into them. And then of course I think kind of an obvious thing would be put some vents on the bottom as well, so that we have somewhere for air to come in, wash over the board, and come out of the top. That'd be the best way to go. Do we really need to put those vents on the very top surface or not? Well, that's not hard for us to find out. We'll just make a configuration where they're located right there, little linear pattern of them, and find out. So that's what I've done. I've taken these and just cloned my study 3 times to each one of those configurations. Use that bulk run to run these things to figure out which one is going to be the coolest. And as you probably guessed, that third option, vents at the bottom and vents on the very top, is going to give me the lowest temperature. It's not a huge difference from having those vents right off the top. So I feel like I could really choose either one of those options to move forward with. And of course, I've got the reports to prove this, and I've got the visuals and animations to show other people. In fact, if you're doing any simulation, it's not a bad time to think about photo rendering and visualize, or moving on to even VR, extended reality type approaches to show other people what the design is going to be, especially with all of these cool colors and animations. So flow simulation can obviously do a lot. I was only able to show you here maybe 2 of them inside these 45 minutes that I used so far, just to talk about general airflow, how to set one of those up, and then of course thermal analysis, which I think electronics are likely to have the most components in them. So I wanted to bring that up. But there is just a wide range of applications. And basically everything that you see here is included inside of the one license that's called Flow Simulation. Right? You have to have a SOLIDWORKS license to run this stuff. It runs inside of SOLIDWORKS, and then you buy Flow Simulation, and it does just about everything I've shown you here, but there are 2 extensions you can buy. Now, these aren't whole new licenses. They're really just extensions, a little bit of the functionality, a bit of the databases. The first one being electronics cooling. Now, of course, I can do electronics cooling with just the Flow Simulation license. I can learn a ton about it just with that. But there's a few things you should know about if you are doing a lot of electronic stuff. One of them is that 2 resistor model you saw me use. It's really good for integrated circuits. Anything where you do have a junction or a board temperature, that model there, the equations for it are in this module. Heat pipes as well. If you're using heat pipes, or if you want this more accurate PCB generator that you saw me open up, so you can put in the number of layers and their copper coverage, you can definitely still just go with a single material or an isotropic material for PCB, but it's nice to have that extra layer of accuracy. Or the equations evolved with Joule heating, right? If I want to put an actual current through some traces, if I want to see if my circuit is going to burn up or have a short, or if I'm going to, burn through some sort of relay, you can do this with Joule heating. And then finally, that enriched database. So you're going to have more fans right out of the box, more materials right out of the box. Of course, you can enter those. You can create your own custom fans, go to your manufacturer and get your fan curve and just copy and paste it in there. But it certainly is nice to have that database. The second way to extend functionality is with the HVAC module. And this really is designed initially for HVAC systems. You're setting up a hospital, you're setting up a bus, and you need to figure out what are the humidities going to be and calculate these human comfort factors that you might use against different regulations like OSHA regulations to prove that, hey, if we put this design in, we're going to have the appropriate humidity and temperatures in these different areas of the building. But really what I see a lot here is the advanced radiation model. So if you really want to take into account the spectrum of light for radiation, that's a reason to go here. Maybe you're doing a light box that has some transparent materials in it. Maybe you're doing an industrial grow light that changes colors. Maybe you're dealing with something in outer space where radiation is a big deal, some satellites. We have customers doing all of these things that actually use the HVAC module for it. And tracer studies are nice as well. They can really help figure out the amount of condensation or the amount of an adjunct that is picked up by a carrier fluid. Not to mention the enriched database that comes with this as well.